So this is actually work by a PhD, Möller, who worked on this since a couple of years, and we are now working in a larger collaboration with Fujitsu Japan on this to solve or to develop a CFD solver for quantum computers. And you might ask, why and what type of quantum computers? Well, we saw a very exciting talk, keynote talk just before the break about reactive CFD. If we just look at classical CFD, so what are the big two challenges? I would say space and time. If we want to do DNS in 3D, we have a very high memory consumption. And if you want to do fine time stepping, then we have very many time steps that we have to do. So these are, I would say, the two grand challenges of CFD. And a possible, I'm very careful, a possible solution could be quantum computers. Because why? Well, there is the possibility to encode log n states in n. Capital N is always the classical one, small n is the quantum one. Information via superposition of states. And well, with another technique inherent to quantum parallelism, we can work on all these 2 to the small n, 2 to the number of qubit, different states simultaneously. There are a lot of catches. We can't get out the information, getting it in. Encoding data is difficult, measuring out is difficult, how to efficiently describe these quantum circuits. So this doesn't come for free, but hypothetically, this is what a quantum computer offers as a kind of plus. And we split this talk into this topic into 2 talks. This is more on the, let's say, conceptual ideas, the mathematics. And then Colleen, who is another PhD of mine, will talk after the next. So the next talk will be about a start-to-end implementation of that in a QLVM software framework. So I already mentioned it. We are not looking at what many people do, macroscopic, Navier-Stokes. We look at the mesoscopic scale, LBM. Why? Because that somehow fits very nicely into how a quantum computer works. So we have this 7-dimensional distribution function living in the physical space, in the velocity space, and the time space, so 7 dimensions. This is kind of making the problem more difficult, but it's a distribution function. And if you have had a look at how quantum computers work, they exploit this. So, and I keep it at this very high level look at LBM. If we let this distribution function alone for a long enough time, it will reach some equilibrium. That's this F equilibrium. Just a quick link, one can recover the macroscopic quantities, density, momentum, energy, by averaging over the velocity space. So then we are back at a 3+1 dimensional space quantity. Very quick derivation. What we do is we take the total derivative of this distribution function. We use kind of some simplifications. Here we end up at the Boltzmann equation and say this should be equal to the, let's say, the collision term. Collision term is responsible for the particle-particle interaction. Here we look at the simplest one, the VGK one. And in just a moment, I will even skip this because at the moment we are looking at the collisionless Boltzmann equation. And what I want to show you is more how this concept works and not that we have a, let's say, high fidelity QLBM code right now. So the first step in LBM is discretizing in the velocity space. So these are the standard stencils that one uses. So D2Q9 is maybe the most widely one in 2D, D3Q27 in 3D. So now we brought it from a 7-dimensional to, again, a 3+1 dimensional problem with discrete velocities. That is what we have here. With the velocities, I denote that by alphas. And then we do some very standard discretization in space and time. Equidistant grids, equidistant time steps, nothing too complicated. And then you can say let's say a vanilla LBM code looks like this. It somehow initializes the data, and then it repeats collision, streaming, boundary treatment for n time steps, and then produces a flow field. And then, I use this terminology, read out from the quantum. I kind of write out something, write out the flow field. For example, we in the last years worked on several of this. We started with this. This was looking at how to stream. Yeah, you could also say this is the passive transport. And we looked at how can we efficiently read out something. Small showstopper, we cannot read out the flow field efficiently. We read out a force. Yeah, so the classical momentum exchange method, we developed a quantum version of that. And then we thought, well, we just have to do collision on top, and then figured out that, yeah, it's not so simple. Yeah, collision needs a very specific encoding, data encoding. I say on my very last slide a few words about that, but for the rest of this talk, we make the life, or our life, a little bit easier. We ignore the collision term. Yeah, don't shoot me. I know this is not real physics, but this talk is more about, yeah, giving you the concept of how a quantum LBM method would look like. Yeah, and so we repeat these two steps and time steps. Yeah. Let me spend some time on data encoding, because that is A, where it starts, and B, one of the big challenges in quantum computing. If you would have a 2D grid like this, yeah, so this here defines one object. These are, we need them later. These are the positions that are either directly outside or directly inside the object. Yeah, and in a classical register, you would say, well, I have maybe 9 velocity components, and I have 8 times 8 in X and Y. Yeah, so you would encode it like this, for example, 576 double, single, whatever. Yeah, so data items. And it would be straightforward to say, well, I encode this quantity in this position in the register. Or you flip it around if you want to have better memory access, but this would be how you do it classically. Well, in quantum, and this is to illustrate why there is this potential saving, we put everything into a quantum register. And yeah, again, capital N is classically, small n is log2 log of that. Yeah, we have this encoding. We have some registers for the grid position in X, some for the grid position in Y, some for the velocity in X, some for the velocity in Y. And if you've never seen this before, it might look like magic. It just means this is a basis state, and this is the basis coefficient relative to the state. Yeah, if you have 3 qubits, you can have 2 to the 3, so 8 different states from 0, 0, 0, 0, 0, 1 up to 1, 1, 1. And you encode the data here. Let me give you this example again. Yeah, we have the same grid, same D2Q9. 10 qubits would be enough to encode all that. Yeah, we need 3, 2 to the 3 is 8, 3 in X, 3 in Y, and it's a plus. It's not a multiply, yeah, because we don't have to encode all of them. This multiply comes from the Kronecker product that we get here. Yeah, and then 2, because we are in 2D, or 2 plus 2 here. And this probability amplitude, yeah, would correspond to this, so the 4th velocity component at this grid position. And I'm saying corresponds to, because this is, of course, normalized. Yeah, we do not have this is equal to, but it is just proportional to up to some normalization constant. Yeah, so letting it look a little bit more complicated, this is now for the generic case in, let's say, 3D. Yeah, this is for the velocity. This is for X, Y, Z. We need some helper variables, or helper register entries. What for? Well, to hold decision variables, for example, are we in an obstacle, yes or no? More precisely, are we, let's say, at a wall, at a corner, at the face of an obstacle, yes or no? I show you some details. And again, don't quote me on that. This is just a very rough calculation how excessive this memory saving could be. If we are in 3D on a 1024 cubed grid, yeah, classically we would have something like this, yeah, something like 29 billion floating point numbers. If we do double precision, would be something like 230 gigabyte. Yeah, fits on a desktop machine, a bigger one, but that's the order of memory we would need. According to this calculation, we need 46 qubits. Disclaimer, these are not the qubits we have today. These are, let's say, perfectly behaving error-corrected qubits. Yeah, so not the one that any vendor offers you today. Yeah? But we are, from the very beginning, we decided we are not looking at the NISC machines. We look at the perfectly behaving machines that hopefully will come. Okay, so I said one of the challenges is memory consumption. What about compute time? Yeah, can we also reduce the compute time? And well, how with this concept, or with this intrinsic to quantum concept, quantum parallelism? And let me give you a closer look at this discrete velocity. Yeah, so this represents the ancillary qubits. This is the X and Y position in the grid. And this is, yeah, for this, we need 2 bits or qubits per direction. This is in X direction, this is in Y. So this encodes, we stand still. We stand still at any point in place or in space, yeah? This means we go to the right. This means we go to the left, yeah? So the left qubit is always positive, negative. This means go stand still. Yeah, and this gives you a glimpse of an idea how we encode velocities here. So when we want to stream a particle, it just means a particle moves with a velocity in one direction. So if the time step, the grid size is all fine, yeah, then in one time step, it goes from one grid position to the next grid position. Yeah, so here I give some ideas. So this one stays still, okay. This one moves in X direction with a plus, so it will be at the next time step at X plus 1, and so on and so forth. So basically, we just have to move around particles, we have to shift amplitudes from one state to the other. Yeah, and that's what we do. And in quantum, we do it all simultaneously. Yeah, you can't, in the superposition, you can't say, I just want to touch this state. You always touch all states simultaneously. Yeah, that is illustrated here. Yeah, so might look a little bit crazy. This here encodes the grid. This here encodes the direction. This here encodes the velocity. In our case, we have just one velocity bit or qubit in one direction. What we technically do is we detect, are we now streaming? Let's say, are we streaming in the positive, are we streaming in the X direction? That's what we determine here. Okay, if we are streaming in the X direction, and if it is positive, we have a kind of incrementer. An incrementer just moves the amplitude from your perspective from here to there. If we are streaming but in the opposite direction, yes, so this means a knot or a negative knot, yeah, then we decrement, we stream it in the opposite, so in that direction. Yeah, and what you see, the magic behind it is, before we do a quantum Fourier transform and afterwards, and then this incrementer is just a small rotation in the amplitudes, yeah, and then we set it back. Now, what are these auxiliary qubits used for? Yeah, of course, yeah, okay, you saw it here, you have multi-controlled some things, and this block is a bunch of, yeah, quantum gates, see it as micro instructions, yeah. If you always do these multi-controlled, it's expensive. So what we do is we kind of have variables where we store this decision. Yeah, this means, okay, we are now in this particular velocity case. Yeah, so, and then it's just direction plus this pre-calculated decision applied to it. That's one of the examples where the auxiliary qubits are used for. Yeah, okay. So now let's assume the particles all travel. They impinge on an obstacle. So here I have the specular reflection case. Bounce back is very simple. Yeah. What we have to do is we have to detect that this situation happens. And there are several more situations if we are at the corner, for example. And what we then have to do are 2 things. We have to place the particle to the right position. Yeah. So this would just stream here. Okay, we have to place it there. Replacing it is the same shift as before, yeah? Taking it from one position, shifting it, in this case, to X minus 1. And we have to change the flow direction. Well, we are in this situation. We have to be, or have to get into that situation. Well, what does it mean? It means we are flipping 1 bit flipping one bit is, in quantum language, apply an X gate, yeah, a flip. A 0 becomes a 1. And all the other cases work in the same way, that we flip individual bits, or qubits, I should say. Yeah. So, yeah, I said it here. Putting this all together, what we do is we have these multiplied controlled knots for the bit flips, and we have the Draper type adder. That's the shift that I just with the QFT inverse that I just presented before. Okay, this is blurred, shouldn't be. Yeah, these are all the different cases somehow that one has to consider. Yeah, for example, one detects, okay, we are at the wall, we are at a horizontal wall, then we have to do this and this and this things. Yeah, and what I try to illustrate, maybe that's the wrong language, yeah, but we have sequential for loops here over the velocity configurations, yeah, stand still, move left, etc. And then we have parallel, but parallel not in a classical parallel, but really in a quantum parallel. That means we apply one gate to the full state, yeah, that is streaming. And also, yeah, we have a sequential loop over all the cases, a sequential loop over all the velocity configurations, and then do this quantum parallel. And one can somehow parallelize that by kind of adding more auxiliary qubits. Okay, just to show you, we implemented that, but Kali will show much more about this in 2D and 3D. Yeah, so it really streams. It even streams on a more complicated geometry. Yeah, this is specular reflection. This is bounce back. And with that, I want to finish. So this is, of course, just a prototype of a QLBM thing. And the two important things I showed you, yeah, encoding and primitives for streaming, specular reflection, and bounce back. Boundary treatment. Okay, should come, doesn't. Yeah, so this quantum momentum exchange method is something that I couldn't talk about due to time. And here's the big but, a big thing. For collision, one needs a different encoding. This is not as efficient anymore. Yeah, we get some dependency on the number of time steps we need to do. Yeah, but if we are not doing too many time steps, we are still better than classically. And that's the moment where I should stop and say thanks again to our sponsors and to your attention.